In the heart of modern Rome, amidst the noise of traffic and the bustle of tourists, stands a structure that simply should not exist. If you were to walk into the Piazza della Rotonda today, you would be staring at a building that defies the logic of time. It is a massive cylinder capped by a perfect hemispherical dome, a shape so mathematically precise that if the dome were flipped upside down, it would fit perfectly inside the rotunda to create a sphere. For nearly 2,000 years, it has withstood earthquakes, floods, barbarian sacks, and the corrosive urban pollution of the modern era. It is the Pantheon, and the mystery it presents is not just aesthetic, it is a profound engineering puzzle. How is it that the Romans, working without reinforced steel, without modern computers, and without the scientific understanding of physics we possess today, managed to build the largest unreinforced concrete dome in the history of the world? It is a record that stands to this day. No other civilization before them could solve the problem of spanning such a massive space with stone. The Greeks tried and failed with lintels that snapped. The Egyptians relied on forests of columns to hold up their roofs. But the Romans solved the problem of weight, thrust, and gravity in a way that remains bafflingly effective. In this documentary, we will not only explore the history of this masterpiece, but we will also deconstruct the specific engineering breakthroughs that made it possible. We will examine the chemical composition of a lost material technology, the intricate logistics of moving mountains of stone across the Mediterranean, and the hidden structural tricks built into the walls that you cannot see with the naked eye. We will answer the question of how Roman engineers solved a problem no other civilization could: the conquest of interior space. Stay with us until the end, because the secret to this building's survival may actually hold the key to the future of sustainable modern construction. To understand the magnitude of this achievement, we must first look at the context in which it was born. We are in the early 2nd century AD. The Roman Empire is at its absolute zenith, stretching from the rain-soaked moors of Scotland to the burning sands of Syria. The emperor is Hadrian, a man of immense intellect, a traveler, and an amateur architect himself. The original Pantheon, built by Marcus Agrippa during the reign of Augustus, had been destroyed by fire, a common fate in a city built largely of wood and tufa. Hadrian wanted to replace it with something that would not only honor all the gods, the Pantheon, but would also serve as a cosmogram, a physical representation of the universe itself. However, the problem facing Hadrian's architects, likely led by the brilliant Apollodorus of Damascus, was one of physics. To build a temple worthy of the cosmos, they needed a dome. But stone is heavy. In the ancient world, if you wanted a roof, you usually used wooden beams which rot and burn, or you used stone lintels. The problem with stone is that it has incredible compressive strength. It is hard to crush, but very poor tensile strength. If you stretch it or lay it flat across a gap, it snaps. This is why Greek temples are filled with columns. The columns have to be close together to support the heavy stone beams above. Hadrian wanted a clear, open space, 43 meters wide, with no internal columns to block the view. This required a dome. But a dome of that size exerts a terrifying amount of outward thrust. It wants to flatten out, pushing the walls outward until the whole building collapses. This was the challenge: how to contain that thrust without the building tearing itself apart. Can you imagine the pressure on the lead architect? If this structure collapsed during construction, it would not only be a financial disaster, but an embarrassment to the emperor himself. Have you ever tried to build a sandcastle or a house of cards that defied gravity, only to watch it crumble? Write in the comments how you think you would handle the stress of building for an emperor who had the power of life and death. The solution began deep underground. We will now look at the foundation, the unsung hero of Roman engineering. The Romans understood that a structure is only as good as what it stands on. For the Pantheon, the engineers realized that the marshy ground of the Campus Martius was unstable. Before a single brick was laid above ground, they dug a trench nearly 5 meters deep and poured a massive ring of concrete. This foundation ring is wider than the walls themselves, acting as a snowshoe to distribute the immense weight of the dome, which weighs nearly 5,000 tons, evenly across the soil. Without this heavy, solid base, the Pantheon would have cracked and sunk within a decade. It was a brute force solution, but a necessary one. They were literally anchoring the building to the earth. However, a strong foundation was not enough. The true revolution, and the reason the Romans succeeded where the Greeks could not, lay in their unique material technology. This brings us to the core solution, opus caementitium, or Roman concrete. When we think of concrete today, we think of a gray, utilitarian slurry that dries quickly. Roman concrete was different. It was a composite material that relied on a specific, magical ingredient, pulvis putiolanus, or volcanic ash from the region of Pozzuoli, near Mount Vesuvius. The Romans discovered that when this specific ash was mixed with lime and water, it didn't just dry by evaporation. It underwent a chemical reaction. It formed a mineral structure called aluminum tobermorite. This reaction created a rock-like substance that was not only incredibly strong, but also waterproof. In fact, Roman concrete could set underwater, which is how they built their massive harbors. For the Pantheon, this material allowed the engineers to cast the building as a monolith. Unlike a Greek temple, which is a house of cards made of stacked blocks, the Pantheon is, in essence, one solid, continuous, artificial stone. By pouring concrete into wooden molds, they could create shapes that were impossible to cut from quarry stone. But simply pouring concrete was not the secret. If they had poured the dome using standard concrete, it would have been too heavy, and it would have collapsed under its own weight. This leads us to the structural and design genius of the building. The Roman engineers implemented a system of gradation that is nothing short of brilliant. We must look closely at the walls. The rotunda walls are 6 meters thick. As the building rises, the engineers change the recipe of the concrete. At the bottom, where the pressure is highest, the aggregate, the stones mixed into the cement, consists of heavy, dense travertine and basalt. This provided maximum strength. As the walls rose, they switched to lighter materials, brick and tufa. By the time they reached the dome itself, the engineering became even more refined. The dome is not a uniform thickness, it tapers. At the base of the dome, the concrete is thick. But as it curves inward toward the top, the concrete layer becomes thinner. More importantly, the aggregate changes again. For the highest part of the dome, the Romans used pumice, an incredibly light, air-filled volcanic stone that floats on water. They also mixed in crushed pottery vessels. This meant that the top of the dome was significantly lighter than the bottom, reducing the deadly outward thrust that threatened to collapse the walls. It is a masterful display of material science. They didn't just build a wall, They engineered the density of the wall to fight gravity. Can you imagine what would have happened if they had used the heavy basalt stone at the top of the dome instead of the bottom? The entire structure would likely have imploded before the scaffolding was even removed. Furthermore, we must examine the internal layout and the social logic of the space. The Pantheon was not just a feat of engineering, it was a feat of political theater. When you enter the Pantheon, you pass through a traditional rectangular Greek portico. This was intentional. It was meant to look like a standard temple. But when you cross the threshold, the space explodes into a circle. This transition from the rectangular, earthly, to the circular, heavenly, was a psychological shock to the ancient visitor. The interior creates a perfect sphere. The height from the floor to the oculus is exactly the same as the diameter of the dome, 43.3 meters. In the Roman mind, the sphere represented the heavens, and the circle represented eternity. By holding court in this building, the emperor was placing himself at the center of the cosmos. The layout reinforced the social hierarchy, the gods above, the emperor below them, and the people surrounding him. The architecture served the state. The lack of internal supports meant that nothing obstructed the view of the emperor or the statues of the gods. It was a unifying space, designed to make everyone inside feel part of a single, coherent whole. But how did they actually build it? We will now turn to the materials, logistics, and labor, which were on a scale that rivals the pyramids of Giza. The construction of the Pantheon required resources from across the entire Mediterranean. Consider the 16 massive granite columns in the portico. Each one is a single monolith, one piece of stone weighing 60 tons. These were not quarried in Italy. They came from Mons Claudianus in the remote eastern desert of Egypt. Let us pause and consider the logistics of this for a moment. How long do you think it would take to move a 60-ton rock from a desert in Egypt to the center of Rome, using only wooden rollers, ropes, and wind? It is a staggering thought. Thousands of workers, likely a mix of skilled paid laborers and slaves, had to quarry these stones. They then dragged them 100 kilometers across the desert to the Nile River. There, they were loaded onto special barges. They floated down the Nile to the Mediterranean, were transferred to massive, heavy transport ships, and sailed across the sea to the port of Ostia. From Ostia, they were dragged up the Tiber River against the current, unloaded, and rolled through the narrow streets of Rome to the construction site. And remember, they did not have cranes powered by diesel. They used wooden treadwheel cranes, powered by men walking inside a wheel, to lift these columns upright. The risk of breaking one was immense. If a column cracked, years of work would be wasted. The fact that all 16 stand there today is a testament to an organizational capacity that disappeared after the fall of Rome and did not return to Europe for 1,000 years. However, the visible parts of the Pantheon are only half the story. We will now reveal the hidden systems that keep the building standing. If you were to strip away the brick facing and the plaster from the outside of the rotunda, you would see a complex web of relieving arches. The Roman engineers knew that the walls could not just be solid mass. They had to channel the weight. Embedded within the 6-meter-thick walls are brick arches that act like a skeleton. These arches divert the weight of the dome down onto massive piers, essentially pillars hidden inside the wall, rather than allowing the weight to press down on the hollow niches where statues stood. It is a precursor to the Gothic flying buttress, but hidden inside the masonry. Additionally, there is a hidden system right under your feet. The floor of the Pantheon is slightly convex. it bulges in the center. This is not a mistake. Because the oculus, the great eye in the ceiling, is open to the sky, it rains inside the building. The floor is slanted so that water flows to the edges and into a complex drainage system of pipes underneath the marble, carrying the water away to the Tiber. Even the weather was accounted for in the engineering plan. Speaking of the oculus, this is the special feature that truly sets the Pantheon apart. It is a hole, 9 meters wide, at the very apex of the dome. A modern engineer might look at this and see a weakness. You are taking away the keystone, the central point where the arches usually meet. But for the Romans, the oculus was the key to the stability. By leaving the center open, they removed the heaviest part of the dome. There is zero weight at the very top. Instead, they built a compression ring of ultra-strong brick and concrete around the opening. This ring acts like the rim of a bicycle wheel, holding the compression forces tight. The oculus also provided the only light source. As the sun moves across the sky, a shaft of light tracks across the interior of the dome like a celestial clock. It is a piece of engineering that doubles as a religious experience. Now, a question often arises. If the Romans could build this in 125 AD, why don't we build things like this today? Why can we not recreate the Pantheon exactly as it is? The answer is complex. Physically, we could, but economically and legally, we can't. Today, we rely on reinforced concrete with steel bars, rebar inside. Steel is great for tension, allowing us to build flat slabs and thin towers. However, steel rusts. When steel rusts, it expands and cracks the concrete. This is why modern bridges and buildings have a lifespan of about 50 to 100 years before they need major repairs. The Pantheon has no steel. It relies entirely on compression. Because there is no metal inside to rust, the concrete remains chemically stable. In fact, recent studies show that Roman concrete can heal itself. When cracks form, rainwater reacts with unhydrated lime clasts in the mixture to seal the crack. We don't build this way today because it is incredibly slow and labor-intensive. The walls of the Pantheon took years to cure. The thick walls eat up valuable real estate space. Modern developers want thin walls and fast construction. We have traded the longevity of the Romans for the efficiency of the modern market. Stay with us, because we will return to this idea of longevity in our conclusion. Ultimately, the Pantheon teaches us a vital lesson about modern relevance. In an age of disposable architecture and planned obsolescence, Roman engineering stands as a rebuke to our short-term thinking. They built with the intention of eternity. They solved the problem of spanning space not by fighting nature, but by understanding the nature of their materials. They matched the density of the stone to the forces of gravity. They utilized waste products, volcanic ash, to create the most durable building material in history. The problem no other civilization could solve was not just how to build a dome. It was how to build a dome that would outlive the civilization that built it. The Egyptians built mountains of stone. The Romans built a machine of space and concrete that survived the fall of their empire, the Dark Ages, and the Renaissance, to inspire architects like Brunelleschi and Michelangelo. When we look at the Pantheon today, we are not just seeing a temple. We are looking at a victory of human intellect over the limitations of the material world. It is a reminder that great engineering requires not just mathematics, but foresight, patience, and a deep understanding of the Earth itself. So, the next time you see a modern concrete building cracking after 30 years, remember the Pantheon. Remember the volcanic ash, the pumice, and the relieving arches hidden in the walls. What do you think is the most impressive part of this structure? Is it the transport of the Egyptian columns or the chemistry of the concrete? Write your thoughts in the comments below and let us know if you think we should return to using unreinforced concrete for our public buildings. If you enjoyed this deep dive into Roman engineering, make sure to subscribe and hit the bell icon so you don't miss our next documentary, where we might explore the hidden aqueducts that kept this massive city alive. Thank you for watching.